A novel self-supervised pre-training protocol for landmark detection in X-ray images is introduced, leveraging diffusion models to address the challenge of data scarcity in the medical domain. This approach offers an alternative to ImageNet supervised pre-training and state-of-the-art self-supervised pre-trainings, which often require large annotated datasets. By utilizing diffusion models, the proposed framework achieves accurate landmark detection with a minimal number of annotated training images. The framework's performance is evaluated on 3 popular X-ray benchmark datasets, where it outperforms existing methods. This study is the first to explore the application of diffusion models for self-supervised learning in landmark detection, providing a valuable pre-training approach for few-shot regimes. The proposed protocol mitigates data scarcity by leveraging the generative capabilities of diffusion models to learn robust representations from unannotated data. The use of diffusion models enables the framework to learn complex patterns and relationships in X-ray images, allowing for accurate landmark detection with limited annotated data. This approach has significant implications for medical imaging applications, where annotated data is often scarce and expensive to obtain. The proposed framework offers a promising solution for improving landmark detection accuracy in resource-constrained settings. The study's findings demonstrate the effectiveness of the proposed protocol in addressing data scarcity and improving landmark detection performance. The results highlight the potential of diffusion models for self-supervised learning in medical imaging applications, offering a valuable contribution to the field. The authors introduce a novel few-shot self-supervised pre-training method that utilizes denoising diffusion probabilistic models, DDPMs, for landmark detection in X-ray images, where annotated images and labels are scarce. This pioneering work applies diffusion models to self-supervision in landmark detection. The authors compare their approach with state-of-the-art alternatives, including ImageNet supervised pre-training, MoCo v3, SIM-CLR v2, and Dino self-supervised pre-training, in terms of performance and robustness under varying labeled training samples. In the context of landmark detection, existing works have primarily addressed data scarcity by leveraging transfer learning techniques. However, the authors examine the impact of self-supervised pre-training with diffusion models on landmark detection for X-ray images in a realistic scenario with limited annotations and images. The proposed approach is illustrated in Figure 1, which depicts a 2-step methodology. First, a DDPM is pre-trained on the training set in a self-supervised fashion without annotations, and subsequently, the model is fine-tuned on the labeled training set for the downstream task. The authors employ a denoising diffusion probabilistic model, DDPM, for self-supervised learning, SSL, pre-training to tackle the landmark detection task. The DDPM-U-Net architecture is used as a predictive model for noise, where it receives batches of images alongside their respective diffusion time steps during pre-training. This allows the model to learn rich and general features for the downstream task of landmark detection. In the second stage, the pre-trained U-Net model is fine-tuned for landmark detection in a few-shot regime, using a few available annotated data for the downstream task. This step requires only modifying the final classification layer to align with the number of landmarks to be predicted. The authors employ a self-supervised strategy in the first stage, with no annotations, and a supervised approach in the second phase, providing the model with ground truth heat maps for each landmark to be predicted. The experimental setup is described, including the datasets used, which comprise chest X-rays, cephalometric X-rays, and hand X-rays. The datasets are split into training, validation, and testing sets to ensure clarity and reproducibility in the experiments. The implementation details are also provided, including the use of a single NVIDIA A30 GPU with 24 GB of RAM, Python 3.10, and PyTorch 2.1.0. The datasets are composed as follows. The chest dataset consists of 279 images, with 6 manually annotated landmarks per image. The cephalometric dataset contains 400 images, with 19 landmarks annotated on each image, and the hand dataset comprises 909 images, with 37 manually labeled landmarks. The authors evaluate their model's performance by pixel distance using the annotated landmarks, and compute physical distance using the estimate made by Payer et al. 34, for the hand dataset. The authors propose a self-supervised learning approach using a diffusion model for landmark detection in X-ray images. The datasets employed include chest, cephalometric, and hand, each with 6, 19, and 37 annotated landmarks, respectively, as shown in Figure 2. Data preprocessing involves resizing images to 256 by 256 pixels and normalizing them to a 0-1 range, followed by random augmentations during training. In the pre-training stage, the denoising diffusion probabilistic model, DDPM, is trained with a batch size of 4, using gradient accumulation every 8 batches, for 10,000 iterations. The training process involves 500 diffusion steps with a linear noise schedule, and the model weights are saved at iterations 4,000, 6,000, 8,000, and 10,000 for comparison during fine-tuning. The AtomW optimizer is used with a learning rate of 1e4, and exponential moving average is applied to model parameters with a decay factor of 0.995. The mean squared error is employed as the loss function. The DDPM-U-Net architecture features a multi-scale approach with channel multipliers, 1, 2, 4, 8, incorporating attention mechanisms at a resolution of 32, with 4 attention heads per channel, and includes 4 residual blocks at each resolution level. In the fine-tuning stage, the model is trained for 200 epochs using the AtomW optimizer, with an early stopping criterion, and a reduce LR on plateau scheduler to adjust the learning rate based on the validation loss. The evaluation metrics used to assess the performance of landmark detection algorithms are mean radial error, MRE, and success detection rate, SDR, which are widely used in the field. The MRE measures the accuracy of predicted landmarks by calculating the average Euclidean distance to the corresponding ground truth landmarks, while the SDR evaluates robustness by indicating the percentage of predicted landmarks that fall within a certain threshold distance from the actual landmarks. The experimental results and analysis of the proposed method, which combines self-supervised learning with diffusion models for landmark detection, are presented. The impact of the number of pre-training iterations for the diffusion model on the downstream landmark detection task is investigated. Experiments are conducted with 4,000, 6,000, 8,000, and 10,000 pre-training iterations, and the performance is evaluated on the validation sets of the chest, cephalometric, and hand datasets using the mean radial error, MRE, metric. The results show that the pre-training process is robust, except for the 4,000 iteration case, where the model is still learning crucial data features. The optimal number of pre-training iterations for each dataset is selected: 6,000 for the chest dataset, 8,000 for the cephalometric dataset, and 8,000 for the hand dataset. The performance of the proposed method is evaluated on the downstream landmark detection task, comparing it with supervised ImageNet pre-training and state-of-the-art self-supervised learning methods, including MoCo-V3, SimCLR-V2, and Dino. The results demonstrate that the proposed method outperforms the competing methods across different numbers of labeled training samples, up to 50, in all 3 datasets. The effectiveness of the diffusion model in learning robust representations from unlabeled data is attributed to the performance gains. A visual representation of the method's performance is provided, displaying the prediction heat maps for each dataset with 10 labeled samples. The results highlight the advantages of the proposed method, particularly in low data regimes, which is crucial for medical imaging applications where labeled data is often scarce. The research paper introduces a groundbreaking approach to landmark detection in medical imaging, leveraging self-supervised pre-training with a diffusion model, DDPM. This method is tailored for situations where high-quality annotated images are scarce, a common challenge in medical imaging contexts. The proposed method significantly surpasses other state-of-the-art pre-training models such as ImageNet, MoCo-V3, SimCLR-V2, and Dino in terms of mean root mean square error, MRE, and success detection rate, SDR, across different datasets, including chest, cephalometric, and hand. The results demonstrate that the DDPM self-supervised pre-training method can achieve superior performance with as few as 1 labeled sample, showcasing its efficacy in low data scenarios. For instance, in the chest dataset, The MRE is reduced by 89.6% compared to ImageNet and 76.8% compared to Dino when using only one labeled sample. Similarly, in the cephalometric and hand datasets, the proposed method consistently outperforms other models, even as the number of labeled samples increases. Furthermore, the study explores the impact of different pre-training datasets on the model's performance. It was found that fine-tuning the best DDPM model pre-trained on a larger dataset, hand, on smaller datasets, chest and cephalometric, further enhances the model's performance, suggesting that the choice of pre-training dataset can significantly influence the model's accuracy in landmark detection tasks. Overall, the paper presents a promising solution for improving landmark detection in medical imaging, leveraging self-supervised learning and diffusion models to achieve state-of-the-art results in low-data scenarios. This has significant implications for the development of more accurate and efficient medical imaging analysis tools. In this study, researchers compare the performance of landmark detection tests on cephalometric and hand datasets using their proposed diffusion-based denoising probabilistic model, DDPM, self-supervised pre-training method. They also compare it with other pre-training methods such as ImageNet, MoCoV3, SimCLRV2, and Dino. The results are presented in Tables 2 and 3. Table 2 shows that the DDPM method consistently outperforms other methods in the cephalometric dataset, achieving lower mean root error, MRE, and higher success detection rate, SDR, across all scenarios, regardless of the number of labeled training images. Similarly, Table 3 demonstrates the superior performance of the DDPM method in the hand dataset, with lower MRE and higher SDR compared to the other methods, regardless of the number of labeled training images. The authors also explore the effectiveness of using a larger in-domain dataset, hand, for pre-training in scenarios with limited target task data. Table 4 reveals that using a model pre-trained on the hand dataset for the chest landmark detection task yields better results compared to a model pre-trained on the chest dataset itself for most training samples quantity scenarios. Overall, the experiments demonstrate the effectiveness of the proposed DDPM self-supervised pre-training method for landmark detection tasks, particularly in scenarios with limited labeled data. This suggests that the DDPM method could be a valuable tool for improving the accuracy and efficiency of landmark detection in various domains. This section of the research paper presents a comparative analysis between the proposed pre-training method utilizing a diffusion model and other self-supervised and ImageNet pre-training approaches in landmark detection tasks for chest, cephalometric, and hand X-ray images. Figure 4 illustrates that the proposed method consistently outperforms other pre-training methods across different numbers of labeled training samples. Table 4 provides a detailed comparison of landmark detection performance on the hand dataset, pre-trained on the hand dataset and fine-tuned on the chest and cephalometric datasets, with varying numbers of labeled training images. The proposed method demonstrates superior performance in terms of mean root mean square error, MRE, and success detection rate, SDR, metrics, even when using only a limited number of labeled training samples. The authors emphasize the value of in-domain pre-training using their approach, particularly in real-world scenarios where data and label availability are limited. They also highlight the focus on label-efficient pre-training to minimize computational resource usage, as training diffusion models on large in-labeled datasets can be resource-intensive. The paper concludes by discussing the challenges posed by data scarcity in medical image analysis and the potential of the proposed pre-training approach to address these challenges. The authors emphasize the effectiveness of their method in leveraging self-supervision with DDPM for landmark detection tasks in X-ray images, outperforming state-of-the-art pre-training techniques like ImageNet. Landmark detection in X-ray images poses significant challenges due to data scarcity. To address this, researchers have explored self-supervised learning, SSL, pre-training with a diffusion model. A novel approach is proposed, leveraging a UNet-based denoising diffusion probabilistic model, DDPM, for landmark detection. The UNet-based DDPM model is pre-trained on large, unannotated datasets and fine-tuned on smaller, annotated datasets. This approach enables the model to learn robust representations from large datasets and adapt to specific landmark detection tasks with limited annotated data. State-of-the-art methods for landmark detection, including deep learning techniques such as convolutional neural networks, CNNs, and graph convolutional networks, GCNs, are compared to the proposed approach. These methods have demonstrated promising results but often require large annotated datasets. The proposed UNet-based DDPM model is evaluated on various landmark detection tasks and demonstrates competitive performance with state-of-the-art methods. The results highlight the potential of self-supervised learning pre-training with diffusion models for landmark detection in X-ray images, even in the presence of data scarcity. Key findings include improved performance on landmark detection tasks with limited annotated data and the ability to learn robust representations from large unannotated datasets. The approach also demonstrates adaptability to various landmark detection tasks. Limitations of the study include the potential for overfitting during fine-tuning and the need for additional computational resources for pre-training the UNet-based DDPM model. Future work may involve exploring alternative architectures and training strategies to address these limitations. Anatomical landmark detection, a crucial task in medical imaging, has witnessed significant advancements through the integration of self-supervised learning in diffusion models. Existing studies have successfully employed self-supervised learning for medical image classification, leveraging transfer learning to overcome the limitations of labeled data. For instance, 17, 18, and 19 demonstrate the efficacy of self-supervised learning in medical imaging tasks, where labeled data is scarce. Self-supervised learning enables the model to learn representations from unlabeled data, which can then be fine-tuned for downstream tasks, such as anatomical landmark detection. This approach has been particularly effective in medical imaging, where annotations are time-consuming and expensive to obtain. By leveraging large amounts of unlabeled medical images, self-supervised learning can learn meaningful representations that capture anatomical structures and relationships. Diffusion models, another key component in this framework, have shown promise in modeling complex distributions of medical images. These models consist of a series of transformations that progressively refine the input noise signal, ultimately generating realistic images that capture the underlying anatomical structures. By combining self-supervised learning with diffusion models, the authors propose a novel approach for anatomical landmark detection that can learn robust and accurate representations from unlabeled medical images. The authors also discuss the potential of this approach for various medical imaging applications, including image registration, segmentation, and disease diagnosis. By leveraging the strengths of self-supervised learning in diffusion models, this framework has the potential to revolutionize the field of medical imaging, enabling accurate and robust anatomical landmark detection without relying on extensive labeled data. In the realm of medical image analysis, landmark detection is a crucial task that has garnered significant attention in recent years. This paper introduces a novel approach to self-supervised learning, SSL, pre-training for landmark detection, leveraging diffusion models. The inspiration behind this method stems from the success of diffusion models in generating high-quality medical images, surpassing generative adversarial networks, GANs. The authors acknowledge the importance of landmark detection, citing previous research that employed anatomical atlases with non-rigid registration for lung segmentation in chest radiographs. They also reference a benchmark for comparing dental radiography analysis algorithms, which highlights the importance of accurate landmark localization. To address this challenge, the authors propose a novel SSL pre-training method that integrates diffusion models with heat map regression-based convolutional neural networks, CNNs, for landmark localization. This approach is motivated by the idea of integrating spatial configuration into heat map regression-based CNNs, which has been shown to improve landmark localization accuracy. The authors utilize PyTorch implementations of SSL methods and segmentation models to facilitate their approach. They provide a comprehensive list of relevant techniques and algorithms used in their study, including SIM-CLR, MoCo, and SWAV, which are state-of-the-art SSL methods. The proposed method is evaluated on several datasets, demonstrating improved performance compared to existing landmark detection algorithms. The authors also discuss potential limitations and future directions for their approach, such as exploring different architectures and loss functions to further enhance accuracy. Overall, This paper presents a promising new approach to landmark detection in medical images, leveraging the power of diffusion models and SSL pre-training. By integrating spatial configuration into heat map regression-based CNNs, the authors aim to improve the accuracy and efficiency of landmark localization, ultimately enhancing the quality of medical image analysis.